Welcome everyone to the seminar. Today we have Jason with us, distinguished scientist and researcher, PhD from MIT, and then worked at Weary, and is now the formalizing transformers team, and maybe is going to tell us what they do. And yeah, really excited about your presentation today, so let's get on to one. We never had that, people.
Thanks, everyone. Yeah, so I've been working on this stuff for like 6 months or so, but this is the first time I am actually talking to a crowd about it. So I'm super interested in feedback and questions, what stuff makes sense, what stuff doesn't make sense. Please interrupt me throughout and ask whatever questions you have, or be like, that made sense, that didn't make sense, go deeper here, this bit is boring, anything you have. And my goal on this is sort of a tutorial-ish shaped thing on the proof-based frames for mechanistic interpretability. This talk in 3 bullet points. If you take nothing away but this is the slide to focus on. The motivation is that if we got AGI tomorrow, I don't think we'd be able to use it for mechinterp. I don't think we'd be able to trust what it says to be either faithful explanations nor sufficient. And we wouldn't be able to scalably automate the discovery of mechanistic explanation. And the solution that I'm proposing here is getting trustworthiness via math, which in this case means formal proof. And the remaining bottleneck, which we'll get to towards the end of the talk, if we have time, is going to be unstructured noise. Do I need to point to?
Yeah.
Okay, why mechinterp? I imagine a bunch of you probably already have some sort of belief about why mechinterp might be useful, or maybe might be not useful. In AI alignment, it might help. The standard answers might help with catching deception, with mechanistic anomaly detection, adversarial training, eliciting latent knowledge, providing feedback. I'm going to not go into any of the details here. Feel free to chat with me about it after. The actual causal historical reason in my case is that I saw Neil Nanda's modular arithmetic grokking, and I thought it was cool, and I was like, oh, I should play with this stuff. What is mechanistic? The intuition that I think most people rely on for mechanistic is bottom up. Chrysola says mechanistic interpretability seeks to reverse engineer neural networks, similar to how one might reverse engineer a compiled binary program. Neil says mechanistic refers to the emphasis on trying to understand the actual mechanisms and algorithms that compose the network. I want to point out that both of these are actually about faithfulness of the mechanism, not about mechanistic itself. They're about how closely the mechanisms you have in your explanation actually correspond to the mechanisms that the model uses. And all of the existing methods for evaluating mechanistic interpretations focus on faithfulness. This includes causal scrubbing, activation patching, path patching. And we have nothing, as far as I can tell, for the level of mechanistic detail. This is a problem because the existing metrics are extremely easy to good-hard. Consider the brute force explanation, where you say, I ran the model. You list out all of the inputs that you care about, or all of the ones that are relevant to whatever property you're trying to establish. You record a trace of running the model on all of those inputs. And you say, look, it has the property I desire. This is 100% faithful. It exactly matches the model. It is 100% bottom up. It is also 100% useless for most applications. And it's also intuitively unsatisfactory. And this is very important if we ever want to automate interpretability. If we want to have a metric that we pour optimization power to optimize against, it needs to be the case that it's not trivially easy to good-hard against. The thing that went wrong here, 2 things that went wrong at least, are that this explanation, the brute force explanation, is infeasible to produce, and that it doesn't match our intuition on mechanistic. I claim that these have a common cause, that the explanation is too long. It doesn't fit in your head. And the intuition here is that the more mechanistic your understanding is, the more you should be able to compact your explanation of the behavior. There is a second problem, a little bit more technical, which is that the existing metrics are pretty limited in what hypotheses they permit. in some sense, they're fairly general. They let you pick out any computational subgraph of your network. But they're also pretty limited in that you can't do something, for example, like the interpretation that you do in the modular arithmetic grokking paper. If you're familiar with that, you can't sort of easily mix and match arbitrary computational primitives and still use the method for establishing faithfulness. The aesthetic that I want to push this frame from is, can we get away with minimalism? Now we're transitioning from the first bullet point of how do we sort of setting up the problem of establishing trust in automating Mechinterp into what I'm proposing as a possible solution here. What I mean by get away with minimalism is we say mechanistic detail is proportional to 1 over the description length of a formal proof. Consider theorem statements where you're just saying that a particular model achieves a certain level of performance on some task and expectation. And does this have a laser pointer? But it doesn't.
It does. I think it wouldn't show.
Doesn't show on the screen. Great. Okay. So this is expectation of f of the inputs and the model outputs is greater than some bound. And the goal here, there's 2 ways to look at it. You can minimize the proof length in any formal system for a fixed bound, or you can try to maximize the bound B for a fixed proof length. And how much does this give us? I claim it gives us almost everything we want with regards to mechanistic detail. Diving a little bit deeper, what do I mean by proof? Really, you can use any formal proof system you want, and then you just measure the time that it takes to check your proof certificate. But the proofs in particular that seem to work well with concrete transformers are that you split the proof into 2 parts. One of them is a proof that a particular computation C, which you have to generate, that's sort of the bulk of your, or like that's a significant chunk of your mechanistic explanation, that when you run that computation C on any model's weights, it produces a valid bound for that model's performance. And this is a proof of implication. This is sort of the proof that right now you would do on pen and paper by hand or in a proof checker that sort of contains all of the explanation that is not specific to your model, to your model's weights. And then you combine that with a trace of running the computation C on your particular model to validate that it gives the bound B. And this is the part of the proof that is going to dominate the length in almost all cases, because notably it needs to include a listing of all of the weights of your model. And just listing out all the weights of your model is probably going to be longer than any pen and paper proof you make about that's parametric over model weights. Okay, I want to pause for a moment before I go through this slide. It feels like I have sped through the introduction and context setup. No one has interrupted me with that makes sense, that doesn't make sense, questions. Yeah.
Question. So the part. Oh no, wait.
So the second part is about your specific model, and the first part is about the architecture. So yeah, so my intuition comes from thinking about the brute force explanation. There's a sense in which, right, there's some sense in which you might call it mechanistic because it matches the model exactly. This is the bottom-up intuition. But I think the most that you can say about it is that however much mechanism it has in it, that matches exactly what's happening. There's a faithfulness of the mechanism, but it doesn't have a high degree of understanding of the mechanism. Yes, so that's what proving does. Good question. When we're saying we want a proof in a formal proof system, where part of it needs to list out the model's weights, it needs to match what the model is doing in some way. The reason that I'm calling this minimalist is that I'm not saying explicitly how how you find the match between the mechanism you're claiming and the underlying model. I'm not saying how exactly you read the mechanism off the proof. I'm saying if we optimize real hard on this metric, even if we very hard on this metric, the claim that I'm pushing, or the hypothesis that I have, is that we should be able to extract from such a compact proof the mechanism and how it corresponds.
Adria, can you hear us?
Loud and clear.
Great. You have a question?
Yeah, I guess, like, why do we care about proof length particularly, as opposed to like ease of verifying? Well, I guess is it a proxy for ease of verifying the thing that proves that the small circuit is the same as the model or something? I guess, like, the computation, because the computation C that you have here seems pretty hard to specify, right? It has to be like a fully automatic interpretability thing.
Yeah.
Or
okay, let me say a couple things about that. And we'll see if they answer what I think your question is.
okay.
So when I say proof length, I do actually mean length of the trace of verifying the proof. If you, like, I'm not going to consider it a proof if you have to spend a lot of time, like much longer than the proof is long, verifying that it's a valid proof. So it is about how hard is it to verify the sort of the explanation that you have. As far as the particular computation C, the way that the examples that I have for this, I'm getting a little bit ahead of myself, but I will highlight the sorts of things that you do in this computation. One thing you could do is you could say, these are the important sequences. I will check the model's behavior on these sequences. And if it gets these right, then I have a pen and paper proof that it gets a much larger fraction of them right. Another computation could be, I multiplied out these matrices, I took max over here, and I took min over here, and I combined these numbers in this way, and this gave me a bound. Another computation could be, I performed SVD, or I factored this matrix into a bit in this direction, and the bit that's orthogonal to this direction, and I did something to establish a bound on the orthogonal bit, and then I ran the network on the bit that is the direction that I think is important. I think notably, these do not restrict you to having computational subgraphs as your interpretation of the model. You can have much more general things, which I think is both a benefit. It lets you get sort of like more expressive interpretations. There's sort of no worry that if the model is using alien concepts, they won't be able to be expressed here. On the other hand, it does make it harder to extract the there's another problem that this adds, which is, given a compact proof, how exactly do we extract the interpretation from the compact proof?
Right.
Does that...
Maybe we don't care though about the latter. I think you've convinced me. Thanks.
Yeah.
Can I check my understanding then? Because I thought one of the reasons why compactness would be good would be it's more likely a proxy for the type of ideas that we or a human could use to understand what's happening within the network. And
yeah, so the like strongest form of the claim that I could make here is that human understanding is being able to fit something into your head. Insofar as the primitive language that your head runs is similar to the primitive language of math, then being able to understand a concept is just about it being short enough that you can fit the description into your head. Insofar as there's something that we can't understand that's in math, I would claim that, like, at least if you're like people have general mathematical ability, it's just that it's too long to fit in your head. And insofar as there's concepts that we understand whose description length in math is too long, that could be something like the mathematical language that we chose makes it very hard to express the base concepts that we've somehow fit in our head more compactly. But I think there is this, it's not a perfect correspondence, but I think there's this rough correspondence between the proof being short and humans being able to extract understanding. even if we don't currently have understanding, even if it's like, oh, there's this like very compact bit of the proof, the model seems to be using some alien concept. If it's short enough, my expectation is that we can learn from that, fit it in our heads, and acquire the concept. That's my hope.
Does that mean the goal isn't so much to just get like proofs over certain properties and more like understanding? Because if it's just proofs of certain properties, I can just like if each line I can verify, right? I should be good.
Yeah, so I think there's a couple different things to say here. I think one of them is we should ask, oh, I lost. Yeah, we should ask, why is the brute force explanation unsatisfactory? If you're like, for my explanation, if an oracle came in and told me it has this property on these inputs, and you're like, that's good enough for my application, then indeed, you just need to verify the proof line by line. The only problem with this is that it's infeasible to produce, then it just needs to be compact enough to be feasible to produce. But if your application relies on something other than faithfulness, if you're like, I'm leveraging the understanding, I'm leveraging the fact that we understand this to claim something about out-of-distribution behavior, or about generalization behavior, or about ability to do something downstream with this understanding, then I claim we start caring about compactness. And maybe I'm like overstating the claim here. I like making like strong claims to test them out and play with them and see how far I can push them. But overstating the claim is like, we can, anytime we're like, I want to really deeply understand what's going on, if you try to automate that process, claim, perhaps you can replace that with compactness.
I'll shut up after this, but I just want.
No, I like the question.
Maybe it's a potential bookmark. I think I would at the end maybe want to ask some question of like, what understanding can we even hope to get out of only looking at the model, right? Because if we hope
you mean without the input distribution?
Or without the the deployment environment or something. Because if we're like interested in like how does it generalize in certain environments, like that information is in part in the environment. And like even like I think you're understanding the model enough is like actually.
Yeah, okay, so yeah, we should come back to that. I think that's the way that I would translate is it's a question of how much do we care what the theorem statement is? And I do have a bunch of things to say about that. I'm trying to decide how much. I think there's a big can of worms there, but I think there are interesting things to say about that, and I'm happy to chat about that.
Yeah. Why are we bounding the expected performance, like as opposed to anything else?
I want to claim that this is the most general thing. You're allowed to pick whatever distribution you want over the input data. If you want to pick a uniform distribution, you can do that. Okay, there is a slightly more general thing, which is that if your input distribution data set is infinite and you want to make a universal quantifier over that, the expectation doesn't let you do that. But also I think it's nearly impossible to find a model that actually, like you need to line up your floating point errors perfectly to actually be able to handle sequences of arbitrary length. Otherwise, at some point, the floating point errors are going to compound and the property will start failing. So given that, you can pick whatever distribution. And then you just multiply it by your distribution size, and then you get a count or something, or pick a delta distribution if you only care about one data point. Yeah. Okay. So that was sort of the setup. And the technical part of the talk, I want to talk about our solution in more detail, and at the end, I'll be getting to the sort of remaining bottlenecks, mostly about noise. And for this, I want to give a sort of walk. Short proof length as a definition of mechanistic detail. And here we'll be going through quite algorithmic tasks, the small transformer architecture that I trained on that, the sort of basic model interpretation, the traditional mech-interp on that model, the table of proof size versus tightness of bound, what the proof looks like at each complexity. And here is where I'll really, insofar we still have plenty of time, but here's where I'm going to try to point out where mechanistic detail corresponds to proof length. And then finally, we'll get to the noise problem and conclusion limitations and future work. And the anchor point for most of these, look for how are we tying mechanistic detail with the proof being short. Okay, so the toy task here is max of k, and the graphs that I'll be presenting in this presentation are for k equals 4. You take 4 one-hot encoded numbers, you throw them into the model, you read off the logits at the final sequence position, you take softmax, and you look at what its predicted probability is for the token that is the maximum of those 4 numbers. And that was very quick. Does anyone want me to pause, take this in more? Okay. The actual model setup here you see some equations that I took from Anthropic's mathematical framework. It's a 1-layer, attention-only transformer, no-layer norm, 1 attention head. Vocab size is 64. The hidden dimension is 32. It's a very small model. It has like 10,000 parameters total. A significant portion of that is in embed and unembed. And the basic mech-interp, the traditional mech-interp on this is that you attend more to bigger tokens and you copy. And you can see here on the left, there's the, well, I can really see the quality of the image on the big screen. You can see the attention plot where it's sort of uniform in the query direction. It doesn't matter what query token you have. What really matters is what key token you have, and you attend more to bigger numbers and less to smaller numbers. And then you see in the computation that the diagonal in most cases is bigger than the off-diagonal entries. This is more so for larger numbers. This is an artifact of the distribution of the training set where there aren't that many sequences whose maximum is 5. There's a lot more sequences whose maximum is 64. And the sampling procedure was just pick sequences uniformly. There are approximately 4 proofs that I want to talk about. And I'll go into each of these in details. The thing to focus on in this table is the steep drop between the cubic size proof when you have devocab cubed budget in your computation, where you get 98.4% accuracy. This is the bound on accuracy, lower bound on accuracy. And when you try to go down just a little bit to, instead of devocab cubed, having devocab squared times the model. Sorry, I'm trying, yeah, okay. Devocab squared times the model. You drop to about 55% accuracy, and that's the best that I was able to manage. I tried somewhat hard. I didn't try infinitely hard, so I'm sure you can bump that up a little bit. I think it would be hard to bump it all the way up. Yeah. Yeah, so this is a proof, great question. This is a proof that the expected accuracy on all sequences of length 4 is greater than whatever number is in the bound column.
So this is a procedurally defined task.
Yes, it's, yeah. This is the toy algorithmic task, ground truth labels. Yeah.
Can you clarify how the complexity curve relates to
the number? Yeah, so the thing to focus on in the complexity cost is focus on the sort of leading term difference between each line. And notice that the bounds go down. So the true accuracy of the model is about 99.73%. If you take all sequences of length 4 with numbers between 0 and 63 inclusive, and you ask how many of them does the model get correct, the answer is approximately 99.73%. And you do this is the, yeah, okay. I'll get to how you do this, but roughly you just run the model on all the sequences. And you, for the reason that I picked sequence length 4 is because this is feasible to actually run. It takes a couple minutes. If I went up to length 5, you could still run this. It would take like 60 minutes. It would take like an hour. Length 6 would take like 60 hours. And length 7 would be completely infeasible, I think, to run the brute force proof. So I wanted something that was like pretty easy to run the brute force proof, but still had interesting complexity bounds underneath the brute force proof. And devocab here is 64, and context is 4. And the thing to focus on is sort of what's the exponent of devocab And how does that change between different lines? On the first line, the exponents, we have like d vocab to the 5th times the model. On the second line, we have d vocab cubed. On the third line, it's d vocab squared times the model. On the fourth line, some of this, there's some of the components that we turn the d vocab squared d model into d vocab times d model squared. That's sort of the asymptotic drop in how long the computation takes to run. And then the bound is sort of the best lower bound on accuracy that I managed to get a proof of. Does that make sense? Great. Okay, so going through what do and don't we understand. If we take these equations and we replace them with plots, the thing that we see is that if we're reading off the logic at the final position at index -1, there's this plot, which I promise it's not completely white, but it is small enough that you basically can't see it in comparison to what's happening in the attention circuit. And similarly, the different permutations of the sequence, when you change what's happening position-wise, that's also, it exists, but it's pretty small. The main thing that's happening is this copying. And then over here, for how much attention do you pay to things, there's this part, which is significant, where you're paying more attention to bigger numbers, roughly. And then this part, which is how much attention you pay based on what position things are in. Well, did that get flipped somehow? How interesting. I must have clicked wrong in slides. Very interesting. Okay. This is how much attention you're paying based on different positions, and it's all roughly right around 0. So the position doesn't contribute much to how much attention you're paying to things. It also doesn't contribute much to what you're doing in that position. This is what we get to see when we're doing the brute force proof. The brute force proof is that we take all 16 million sequences or almost 17 million sequences, and we run the model on all of them, and we record the trace. And we're like, how many of them does it get right? The answer is about 99.73%. You can speed this up a little bit by doing clever caching of the model. I think you can get down to d vocab to the 4th times n context with a little bit of fudge factor for dealing with permutations, but it's not entirely clear. But this is roughly, it's at the very least going to be d vocab to the 4th in how long it takes to validate this bound on the accuracy. If we restrict ourselves, we're like, we're not going to allow d vocab to the 4th. We're only going to allow d vocab cubed times n context squared. Because because n context is pretty small. B, because without that, I think we get significantly worse bounds. And I didn't want to have to figure out how to sort of manage the cost between the vocab parts and the context length parts. Here, we only get iteration access to about 1 million sequences. And the key thing that we're relying on for the pen and paper proof is a convexity property of softmax. The mechanistic detail here, the thing to know about this model, is that you get the right answer by paying attention to the maximum token. The more attention you pay to the non-maximum token, in almost all cases, the worse you do. And if you know just this and nothing else, you're like, the thing I'm trying to do is pay as much attention as I can to one token. That's all you need to drop down to cubic, because then the thing that you do is you say, well, I just need to figure out what token is worst to pay attention to, and what's the worst amount, like what's the least attention I pay to the correct token, most attention I pay to the incorrect token. And you can even do a little bit better than that. You can say, sorry, nope, okay, yeah. I was mixing something up in my head. Erase that last sentence. You figure out like what's the worst token for you? What's the most amount of attention you can pay to the wrong token while still getting it right? What's the worst you can do computation-wise on the wrong token while still getting it right? And what you get from this is if you consider token sequences, the way you do this is you say, well, if for any fixed query token, for any fixed maximum token, if it works when all the other tokens are copies of some particular fixed non-max, if that's true for two different non-max tokens, then I can also mix them. And it's also, the model also works for all mixed sequences. I should probably have some slide that visualizes that better. And the thing that we do in this proof is we do a little bit of sort of pessimization over ordering, so we don't need to consider all the different orderings of sequences. We figure out which non-max token works for various numbers of copies of the max token. We're like, well, if you have only one copy of the max token, what's the worst that you can do while still getting it right? If you have 2 copies, if you have 3 copies. And then you combine all those and you can prove that on 98.4% of the sequences, you still get the right answer. So that's pretty good. That's almost 99%. We haven't lost much. If we say we're not allowed to iterate over max, non-max, and query simultaneously, if we need to be subcubic in our iteration, the best I've been able to do is about 55%. Here all I'm doing is I'm sort of playing games with which input sequences I use as representative elements. How I argue that like this is in some sense the worst sequence that we can do over some domain that means that all of the other sequences sort of in the convex region fall into place. And here we get about 65,000 sequences that we can iterate over. And sometimes we want to combine the query token with the key token. Sometimes we want to combine the query token with the max token. Sometimes we want to combine the max token with the key token, or rather the max with the non-max. And in different places, we do different iterations and manage to get 55%. So up to here, sort of the only mechanistic detail that I've been using is you want to pay all of your attention to one thing. There's a best thing. There are worse things. And additionally, in order to get the bound up to 55%, there's also the mechanistic detail about which sort of correlations matter more and which ones matter less. For example, there's some vertical banding here in the query token, where some query tokens are better at paying more attention to bigger numbers than others, which tells us that we sort of care a decent amount. So at least for small separations, we care a decent amount about what query token there is. Whereas the monotonicity in this direction sort of doesn't matter. And so we care a little bit less about what exact non-max token we have. And in particular, because of this monotonicity, we sort of only care about what the non-max token is in terms of a gap. Because if you pay enough less attention to something that's 3 things smaller than the max, because softmax is exponential, you're going to pay even less attention to something that's 5 things smaller than the max. And so you don't need to consider sort of arbitrary subsets of numbers that are smaller than the max. You sort of only need to consider prefixes, and you're like, how much of the prefix can I handle? If we want to compact devocab squared demodel to devocab demodel squared, here's where we sort of start to get a lot more mechanistic detail. This is the first place where something like SVD, singular value decomposition, comes in, where if we SVD the attention matrix, the attention score matrix, we'll see that the first singular value is somewhere around 7,500 or something, 7,000 something. And the next singular value, if I recall correctly, is about 15. So there's really only one thing going on in the attention score, at least if you believe SVD. And you might be tempted here to dive deeper into the analysis. You're like, the key side direction is this nice pattern, and we can fit a line to it. And indeed, it's almost linear. And the query side SVD is mostly constant. So let's also try fitting a line there. And you can try to dive deeper into the analysis. But one of the things to note from the proof frame is that at this level of complexity, when you're just going from dvocab squared dmodel to dvocab dmodel squared, none of that matters. You have enough room in your computation budget to just list out the directions in full. Trying to fit them to a line buys you almost nothing as far as the proof size goes. And remember this point, I'll be coming back to it towards the end as one of the limitations, one of the like places where there's room for improvement on the proofs approach. But the other place where the proofs approach has a problem is in noise. So we take these first singular directions and we factor them out of this matrix, and we're like, dvocab squared dmodel is how long it takes to just compute this matrix, because you're multiplying 4 matrices. If we want to establish a bound without having to multiply 4 matrices, we need to argue something about the remaining singular components without actually multiplying out the matrices, without actually computing the full matrix to compute SVD of it. And it was pointed out to me by Lawrence last night that I had forgotten that you can in fact compute SVD of a product without having to compute the without actually having to multiply out the matrices. But I think you still end up with a bit of a problem, which is that even if you have the SVD of the full thing, you still need to somehow bound what the size of the remainder is without multiplying out your 2 matrices. And one way to visualize this is that we lack mechanistic understanding of how the noise comes to be as small as it is. And I think most mechanistic interpretability sort of glosses over this. They're like, oh, we explain the big thing that's going on, and there's no explanation of how it comes to be that nothing else is big enough to swamp them. Right? How does it come to be that in this product matrix, if you look at any single row and you're like, what's the largest difference between 2 different cells? That's the thing that we end up caring about for the attention score, is a bit under 2. How does it come to be the case that that's the largest difference? And to point out that there's something to say here, if you added structure to these, if you sorted all of these matrices, you get a much larger maximum row diff. I think you end up with something like 2,000. So you can't just do it on the basis of the fact that all the numbers are pretty small. Okay, so the first thought that I had was maybe we can do SVD and multiply the singular values. The maximum row diff is a bit under 2. It is not because the rows are special. If you sort of, in the resulting matrix, if you ignore the row structure and you're just like, what's the largest absolute value of any element? It's about 2. Sorry, it's about 1, and so twice that is about 2. You can upper bound this by root 2 times the first singular value. So in dvocab times dmodel squared time, we can get a bound of 10.7 on this, which is much bigger than 2, but it's not obscenely big. If we go back to look at the scale of the numbers here, notice that this runs from like minus 250 to 250. So really we need to, if we want to be able to say anything at all, we need to say that this is less than like 400. So we have some gap. This is sort of a little bit of an outdated method, but I think still shows that it's non-trivial to establish the noise property. If you're like, well, how do I upper bound the first singular value? What if I take the product of the singular values? That gives you a bound of about 43. If you want to drop down below dvocab dmodel squared, here's where I really have no idea how to do things. Because the best bound that I know how to get on here is the Frobenius norm, where you effectively get the square root of the sum of the squares of the singular values. This is like, what would it be if I concentrated all the singular values into one? What's the like maximally structured version of this? What bound do I get then? And this distributes over product. But the problem is that my 4 matrices, which if I'm at a very stringent complexity bound, I don't have time to multiply out. The bound that I get from this is about 2,700. which is way too big to say anything about.
Like, one question I have is the noise in particular special in this case? Or if you resample the noise with the same magnitude, or like resample noise with the same entries, do you still get like the same amount of noise at the end?
You're like, if you take the distribution and you randomly shuffle, randomly permute everything.
Or like, yeah, when you randomly sample it, or you just like fit a parametric distribution, uniform length, and then you just like sample the uniform.
Yeah, so my expectation is that, so I don't know about uniform versus Gaussian versus something else, but I should definitely try this, but my expectation is that you'd get roughly the same answer here if you resample it. The thing that's hard here, as I understand it, is that there's no structure. And the thing that you're trying to do is you're trying to compactly establish a lack of structure. This is also incidentally why I think all the number theory theorems about primes are so hard, because there's a lot of structure and divisibility. And you're asking questions about what happens when I pull out all the structure that I know about. How do I establish that there's no more hidden structure? And I think this is also why our theory looks at number theory so much in some sense, that it's another case where you want to deal with how do you intelligibly say things about lack of structure. There's another method that I can run here that still requires multiplying out 3 of the matrices, but still gets us dvocab times d model squared, where we get a better bound than from SVD. We can get about 5.7 as our upper bound on 1.85. And roughly what this is, it involves taking the matrix on the right and looking at row differences there, and then taking the absolute value of the matrix on the left and sort of pessimizing over where you have negatives and where you have positives. Okay, so and these altogether drop you down a couple of percentage points. So this gets you down to like 48% or 50%, depending on whether you're doing these approximations on just the QK attention or also on the skip connection, also on the I think, sorry, it's just the QK and the skip connection are both. Okay, conclusions. Proofs are possible, but pretty hard. Man, I should have reordered this slide. I'm going to go a little bit out of order. I think this third one is where I want to start on the conclusions, that proofs can be used as a minimalist grounding of Mechinterp. That if you're confused about something in Mechinterp, you can convert to the proof frame. And I claim, I don't know that I think I haven't presented enough evidence on slides, but from working with this a lot, I claim that this helps understand what's going wrong. This sort of points out where you're glossing over things, where you need to be careful about what you're measuring or what you're claiming. And there's a link between mechanistic understanding and proof length, that shorter proofs require more mechanistic understanding. After you improve the bound tightness for fixed complexity, I've been able to extract some mechanistic detail based on what ways of improving it actually worked and what things didn't. This tells me what directions are important, what correlations are more important, what correlations are less important. And it really seems like the places where I fail to compact the proof are the places where I lack a mechanistic understanding of what's happening. And there have been a couple times where I've then managed to compact the proof more, like in the noise case, where looking at how I managed to compact it, I'm like, I understand a little bit more mechanistically what's going on. So there really does seem to be a tight link between mechanistic understanding and proof length. And this gives us an objective numerical standard for mechanistic detail, one that we can customize to different subcomponents. We can, at least informally, say, I care more about understanding this part of the network than this part. And these parts I'll allow you to be brute forcing. Coming back to the beginning, this also shows that proofs are possible, but that small noise is a problem. When you have no mechanistic understanding of how unstructured things remain structureless, proofs still demand some level of mechanistic explanation. And right now, there's no way to decide how to trade off against this, where with the parts where you care about understanding and the parts where you're like, I'm not fitting that into my head, so I don't actually care about that. So things that are in progress, doing this for larger K, doing this for the modular addition network, sorted list. There's the question of how to solve noise. My hope, and this would need to be tried out, is that if you stick a Lagrange multiplier on the implication part of the proof and the computation part of the proof, and you tweak how much you care about compacting the pen and paper part versus compacting the computation part, this might let you say, I care more about the bits that I understand than the bits that I don't understand. The downside of this is that it makes it a lot more sensitive to what your base mathematical language is and what sort of definitions and theorems you allow yourself to use as primitives. There's another line of approach on this, heuristic arguments, which arc theory is working on, which I think of sort of how do you soundly or relatively soundly, systematically reason about being in the typical case. If we want to make the assumption, like Lawrence was suggesting, that if we resampled it, it doesn't matter. All we need to know is that we're in the typical case. How do you reason about propagation of noise if you grant that we're in the typical case, that we've caught all the structure that we care about? And even more future work, how does this extend to two-layer models? How do we handle layer norm on two-layer models? And I'm interested in integrating this with sparse autoencoders, which I think give us, I had this idea recently that if you do sparse autoencoders on the output of max of K, this might give you the optimal iteration. It might tell you like what sequences you care about the most and which ones you want to group for doing various levels of complexity of your proof. And of course, how do we automate this? How do we turn this grounding, this frame, into an actual automated pipeline for discovering mechanistic interpretations? Thank you all for your attention. Yeah.
Is we've got various mechanistic interpretability methods like automatic psychic discovery. Like, how do we figure out sort of how to evaluate those methods, or like how mechanistic are they, how capable? And that seems like a really strong motivation. And I'm just struggling to connect that to, we've got this hand design proofs about certain parts of the networks. Like, is there a hope still that we're going to be able to apply this kind of approach to analyze something output by ACDC or some of these existing methods? Or are you just going to be like, these have like about 0% because they're like not actually a full explanation?
Yeah, it's a great question. So I think right now it's more of a like grounding frame that you use to like figure out how to evaluate the methods better. You can think of it as like if the methods are giving you confusing things and you're like, I don't understand why it's giving me this. Grounding in the proofs frame, I think, can add insight there. I think the essential challenge to automating things directly from the proof frame is that the language is a lot more expressive. In ACDC, you're just like, what is the computational subgraph? And indeed, if in fact the explanation that you care about is just what's the computational subgraph, then you want a language that's restrictive so that you can search over it. And I think then the main problem with something like using something like ACDC with path patching or activation patching was revealed with causal scrubbing, where they're like not adequate measures of faithfulness. Causal scrubbing is an adequate measure of faithfulness, it seems, but it sort of always tells you that, almost always tells you that your answer is very bad. And if you want to, the thing that proofs gives you here is it gives you a tunable knob, where like, I can say how good I want to be, and then I can ask what size of explanation can I manage to get for that. You always have a starting point, which is the brute force proof. And you can also say, I want this compact an explanation. How good is my bound when I have that compacted an explanation? And so the tuning there is more, there's more tuning that you can do there. I think the other thing is that if we want to go beyond just what is the computational subgraph, then we need to move beyond something that is just search over all the subsets of nodes to include in our circuit. And then the problem becomes, how do we do search over this very general space? Right? I was pushing this as a sort of minimalist aesthetic, which I think makes sense when you want something where you can ground your understanding, where you're like, the problem with understanding what's going on is that if your base theory has too many free parameters, you're like, oh, well, if my interpretation changes based on these free parameters and I have no idea about how to set them, kind of sunk. The sort of minimal proof length has very few free parameters. And so you can more easily understand what's going on. But I think when we're searching for proofs, we like, sure, you can, like, one way that you might do this is you might be like, okay, GPT-6 or GPT-10 or whatever, come up with an explanation and give me a mathematical proof. And then you ask another copy of GPT-7 or whatever, translate that into something that can be checked by a proof system. And this is sort of, I don't know, magical LLM search or something instead of ACDC. But yeah, this is, there's nothing here about how you actually go about finding these explanations.
We have one question from the online audience, Adria.
Thanks, Moritz. Yeah, I'm kind of lost, honestly. Why do you care so much about the cubic case? Like, you know, these matrices, like token by token, in practice, you can always just exhaustively check them. Like, I guess, like, yeah, what I don't understand is, like, yeah, why do you care so much about the cubic case here? It seems like it doesn't scale that badly when you go to large transformers. Or like, what exactly are you thinking about when you say, like, all right, cubic is the barrier to beat?
Yeah, so I think I drive at it almost from the other direction, which is that if you say, okay, cubic is fine, we don't need to go below cubic. The thing to note is that there's
It's easy,
a lot
right?
of what?
It's easy. You like,
I mean, in this network, it's easy to not go beyond cubic, but for
Yeah.
more complicated ones where you have more interesting interactions,
Yeah.
it might be much harder. But the interesting thing that I note about here is that when you're at cubic, there's a lot of level of detail that doesn't show up in the proof, right? You have, the thing that you get out of the proof is that there's always a token that you most want to pay attention to. And
Yeah.
sort of paying attention to other tokens is bad, and so you pessimize over them. But you don't even necessarily get that that's the maximum token. You don't get anything about the query direction being invariant. You don't get anything that looks like we pay more attention to bigger tokens. You don't get anything that looks like we copy.
What do you mean you don't get anything? Like, okay, so I guess, are you assuming that, like, you have an arbitrary cubic proof, and then from that you want to extract the structure of the network? Is that what you're thinking about?
So think about this as red teaming the automated process. I'm claiming that if someone hands me a compact proof, I can extract mechanistic understanding.
Yeah.
And here I'm pointing out that if you hand me a proof that is cubic or larger, I'm not going to be able to extract any of these details that people normally look for in the model.
Okay, yeah. So a random cubic proof does not. Yeah, that makes sense. Okay.
Yeah.
Sure. Thanks for explaining. Doesn't mean I agree.
I should definitely mention red teaming earlier on, because that's like a strong way that how I think about this. That like there's like a lot of work that I do to try to come up with the best bound for a given amount of computation, not because I think it's particularly interesting for this model or even that the techniques that I'm using are particularly interesting, but because if I don't do my honest best at coming up with the sort of least insightful proof that I can get, that I'm not doing a good enough job at sort of red teaming the hypothesis about the connection.
We've got time for one more question if there's one. Otherwise, you've seen Jason around. He will be around later and in the foreseeable future. So if you have any other questions, feel free to ask him. Yeah, any concluding thoughts, questions, remarks?
I can come back to your question from earlier about theorem statements, which was like, what can you say without knowing the environment? And here I'm bringing in my background from programming languages, that in part because proofs are so hard. Even very weak theorem statements get you surprisingly far in that, man, I feel like I need a better example than this. But if you want to know, this model doesn't emit plans for making bombs, or okay, this model doesn't emit plans for killing people. And you're like, man, I don't know how to specify what a plan is. I don't know how to specify what it means to kill someone. This seems really hard. Here's a proxy for that. It's not a great proxy, but it's a not terrible proxy. Take whatever model you have, stick in any arbitrary sequence of up to say 500 tokens, take the first 500 tokens of output, and then feed that back into the model with the question, is this a plan to kill people? Yes or no? And if you can prove that when you feed this back into the model, the answer you get is no, say 95% of the time or whatever. If your proof is compact enough, if you actually understand how it comes to be the case that whatever it spits out is a plan that it thinks won't kill people, I claim that this gets you most of the way understanding why the model does not emit plans that kill people. Notably, if it sticks some random string in the middle that's a stamp, and whenever it sees that stamp, it says, oh no, it's not a plan to kill people, you're like, oh, that's very suspicious. It's only paying attention to this like random string of characters in the middle. Seems like it's not actually like explaining to me why, or like it seems like it's not actually reasoning about why it doesn't kill people. Conversely, if there is some reasoning that's going on about how it accurately evaluates plans and how it generates that, I expect that an algorithmically compound proof explains this. And then if you can fit that explanation in your head, you can say, I don't know exactly what it means to translate plan to kill people into math, but I can take this pile of math and I can say, does that correspond to kill people or not? And you sort of reduce the attack surface from this inscrutable model to this smaller specification or this smaller pile of math about the correspondence between the mathematical understanding and reality. And so to say one more thing, that I think that splitting the environment from the model is both possible and important, that there's some understanding that's like located in the model about what is this model actually doing, and then there's some understanding that's located about the environment that's like, given that the model is doing this sort of thing, how does that build to whatever effects it has?